unsymmetrical fault analysis. Under that, today we are going to discuss about symmetrical component transformation. So for that, first consider the balance system. In the balance system, the algebraic sum of all the balanced three-phase current is 0 at all times. That is IA plus IB plus IC, that is equal to neutral current IN, and that is equal to 0. And for unbalanced system, the algebraic sum of phase current is equal to the neutral current. IA plus IB plus IC equal to IN. The three-phase unbalanced current expressed in terms of sequence current as is IA equal to IA naught, IA plus IA minus. This IA, IB, IC are the phase current. This is a three-phase balance current, and this IA naught is a zero sequence current, IA plus is positive sequence current, and IA minus is negative sequence current. For all the three phases, the sequence current can be represented like this. And now this equation 3 can be rewritten in terms of the A operator. Substituting the A operator here, so IA, that is equal to IA naught plus IA plus IA minus, and in IB, that is equal to IA naught plus A square into IA plus A into IA minus, and IC equal to IA naught plus A into IA plus A square into IA minus. A is an operator to represent the 120-degree phase displacement between the phase current. So the phase currents are IA, IB and IC, and these three phase currents are displaced by 120 degree. To represent this 120 degree phase displacement, we are using an operator called A operator. Next, write the equation 4 in matrix form. So equation 4 is a phase current using a symmetrical component of current and the A operator. Now we are going to convert this equation in matrix form. So the equation 4 can be written in matrix form like this: IA, IB, IC equal to 1, 1, 1, 1 A square A, 1 A square into IA naught, IA plus and IA minus. Now in simplified form, we can represent the phase current IA, IB, IC as IP, and this is a T matrix, transformation matrix T, and this is your symmetrical component current or a sequence current IA naught, IA plus and IA minus, that can be represented as IS. And now from equation 6, the sequence current IS can be written as IS equal to T inverse into IP. So in the previous case, sixth equation, we have seen IP equal to T into IS, and now IS equal to T inverse into IP. So to find this sequence current IA naught, IA plus and IA minus, we need to find the inverse for the transformation matrix. So the transformation matrix T can be represented as 1, 1, 1, 1 A square A, 1 A square. We need to take inverse for this transformation matrix. So for that, consider this T matrix, and T inverse can be represented as adjoint of T divided by determinant of T. So normal matrix inverse we can take, and we can consider the matrix rule also for this sign selection: positive, negative, positive, and negative, positive, negative, and positive, negative, positive. Adjoint of T can be determined using this cofactor of T transpose. So cofactor of T, how to determine the cofactor of T? So first, for this first element, the cofactor will be, you can strike out these terms, the row and column corresponding to the first term, and you can multiply this to A square into A square minus A into A. So A square into A square is A power 4 minus A into A is A square. So A power 4 minus A square, and A power 4 is nothing but A from the A operator rule, and so you can substitute A minus A square. Similarly, for the second term, we need to take minus, and you can strike the column and the row corresponding to the second term, and you can multiply this to 1 into A square minus 1 into A. So A square minus A will be getting, and here you will be having a minus, so it become A minus A square. And the third term, considering the third term, strike out this column and row, and the third term is plus, so you can multiply A minus A square, 1 into A minus 1 into A square, so it become A minus A square. And this first term in the second row, so this term if you are considering, you can strike out the column and the row corresponding to that, and now you can multiply this 1 into A square minus A into 1, that is A square minus A. And this first term, as per matrix rule, it is negative, so A square minus A can be written as A minus A square. And the center term, so you have to strike out the column and the row corresponding to that, it becomes A square minus 1. And the last term A, so you can strike out this and you can write A minus 1, and here you will be having a minus in the matrix rule, so it become 1 minus A. Similarly, this term, strike out column and row, it become A minus A square, 1 into A minus 1 into A square. Similarly, this term, strike out column and row, it become A minus 1, 1 into A minus 1 into 1. So A minus 1, and here in matrix rule you will be having minus, so it become 1 minus A. And the final term, A square, strike out the column and row, so you will be getting A square into 1 minus 1 into 1. So A square minus 1. So this is how you can determine the cofactor matrix of the T matrix. So now you have to take the transpose of this matrix. Replace row by column and column by row, you will get the transpose matrix. The transpose of matrix, that is your adjoint matrix, and this is your complete transpose matrix. Now we need to find the determinant of matrix T. So determinant value from the T matrix you can find 1 into A square minus A into A. A square into A square is A power 4 minus A square, and the second term is minus 1 into A square minus A, and the third term 1 into A minus A square. So normal determination we are doing, and you will be getting the value as 3 into A minus A square. Removing the bracket, it will be getting A power 4 minus A square plus A minus A square. Instead of A power 4, you can substitute A and A square, keep as it is, and here you will be seeing there are 3 A's are there. Okay, so 3A and minus 3A squares are there. So 3A square, taking 3 common, it become 3 into A minus A square. So this is your determinant of the matrix T. Now we can find the inverse of matrix T. T inverse equal to adjoint of T divided by determinant of T. So adjoint of T matrix, you know, this complete matrix divided by the determinant of T, that is 3 into A minus A square. Now you can multiply this 1 by 3 into A minus A square inside the matrix. Okay, take this A minus A square inside the matrix. So what happens in the first term, A minus A square, second term A minus A square, third term also A minus A square. Similarly in the second row and third row, the first term is A minus A square. So all will get cancelled, and this term, that is A square minus 1 and 1 minus A, this term will be divided by A minus A square. We have to do some simplification. A square minus 1 divided by A minus A square. Okay, so you can substitute A cube instead of 1 as per the A operator rule. A square minus, instead of 1 you are substituting A cube divided by A minus A square. In the numerator, take A square as common, it become 1 minus A. In the denominator, take A as common, it become 1 minus A. Cancel this 2 and you will be getting A square by A, that is equal to A. And similarly for the last term, 1 minus A divided by A minus A square. So it is 1 minus A divided by, in the denominator take A as common, it become 1 minus A. So cancel this 2, 1 minus A, it become 1 by A. And for this 1, substitute A cube as per A operator rule, and you can cancel this, you will be getting A square. And this is your complete T inverse matrix. We determine this T inverse matrix in order to obtain the sequence current or symmetrical component of current. So the symmetrical component of current is Is equal to T inverse into Ip, and where Is is Ia naught, Ia plus and Ia minus. Okay, Ia naught, Ia plus, Ia minus equal to this T inverse matrix 1 by 3 into this matrix into Ia, Ib, Ic, where Ia, Ib, Ic are phase current. By expanding this matrix, you will be getting Ia naught equal to 1 by 3 into Ia plus Ib plus Ic, Ia plus equal to 1 by 3 into Ia plus A into Ib plus A square into Ic, and Ia minus equal to 1 by 3 into Ia plus A square Ib plus A into Ic. Okay, in the similar way, you can find the symmetrical component of voltage. So just replacing the current by voltage, Vs equal to T inverse into Vp, and you will be getting this answer, Va naught, Va plus, Va minus equal to the T inverse matrix into Va, Vb and Vc. Expanding this matrix, you will be getting this Va naught, Va plus and Va minus. This is your symmetrical component of voltage, and this is your symmetrical component transformation matrix.